Hello guys, welcome back. Now we get back to the Shattering coefficient function. And before discussing that function, I want to talk to you a little about the Sor-Shelah lemma. This lemma is a way of obtaining an upper bound for the Shattering coefficient. According to this lemma, and this is some PDF files from the Computational Learning Theory, which is a course at the Sine Buffalo Fall 2010. Okay, the lecture, Angu and Scribe Angu. So just to reference, of course. Going down over here, we find the Sor and Shelah lemma. The Sor and Shelah lemma is basically a result, this result. The sum from I starting at 0 up to the Vapnik von X dimension. So this D over here is the Vapnik von X dimension. Okay? And here we have a sample size with M, in this case M elements. And then we compute this, this term over here to find the Shattering coefficient as an upper bound. But actually, it's a very far bound. So over here, I will start coding with you something simple, just to give like a big picture on that. So go back to codes, and here I'm going to start example 2. I will write here for you the Sor-Shelah lemma using an R file as well. So just remember, or just to simplify in our terms, the Shattering coefficient function is this for an n-sized sample. Of course, if it's a 2n, I just change it, okay? And so this is going to be a sum from a sum of a binomial function given my sample size in terms of some D over here, and then that's of course for I starting at 0 and going up to the Vapnik von X dimension D. Maybe you could just write here as VC, okay, as Vapnik von X dimension. So this is going to provide some function, some upper bound function. It is a way of solving this problem. However, it provides like a very far upper bound. If you guys are familiar with computational complexity or maybe time complexity, that's much more widespread, of course. We define a big omega as a tight lower bound for our function, and we define big O as a tight upper bound for our function. And we also have two other notations. We have like a small o, and the small o is a far upper bound, okay? And small omega is a far lower bound. When we talk about this, about the Sor-Shelah lemma, we are talking about a far upper bound. We're talking about this. Okay? So we have a bound, but it's a far upper bound. That's not good, of course, because if it's a far upper bound, it turns out to be unrealistic for most problems we decide to approach. Of course, I believe that we better go for a different solution. In our case, and in this class, we are going to discuss an estimation for the Shattering coefficient function. This is a code I wrote for my book with Moacir Ponti. It's been like, was published in August 2018, which brings together an estimator, but there is a problem with this estimator. It's going to be somehow a far lower bound, but no problem. At least we have the opportunity to discuss it and better understand the Shattering coefficient. I think this is going to help you guys. So I would say that this, my Shattering coefficient estimator, is a far lower bound. So it's not that close as I would like to, but let's start with it. So this guy you guys can compute, of course, using something, for example, as alpha Wolfram, for instance. So we can start using alpha Wolfram. And for instance, just define, okay, the sum of some binomial, I think it's binomial, something like this, of n given some VC dimension. I'm going to write as d over here. Having some I starting at 0 and going up to my VC dimension d. In this case, let's see if it's right or not. I think that's all. And we can just provide some number over here. Yeah, it's in here. Okay, this is the short version of it, of course. So over here we can come up with some dimension. Let's say in my bidimensional space, we knew, and we've seen already, that our Vapnik-Chervon X dimension is 3 because I can shatter a sample with 3 points or 3 examples in every possible way. And you guys will notice we are going to obtain this as our formulation, or in alternate form using gamma functions. And here we have an approximation for the results. Okay? We have just like some examples for different values of d for different Vapnik-Chervon X dimensions. That's interesting, but that's going to be a very far upper bound. Actually, this is really far, and this is a far lower bound, but it's closer than this in many senses. Let's discuss it. So this is a code I provided with the book, and we've got like some interesting stuff over here. Here I have a variable that I'm going to use as a matrix, just to save up all intermediate results, okay? I'm going to print something out, which is, okay, this is my sample size, and this is the number of different classifications found for that particular sample size. You guys might remember that we are interested in cutting the space in as many as possible ways. So my point is, we are going to start with some sample size. Take a look over here. We start with our sample size I over here in n start, and we go up to n end. Our n start is 1 at the beginning. That's a default parameter, and we go up to 100. Of course, you can go up to like less than 100. We're gonna see the impacts of using like a 100. This is our sample. We start with a new sample with a matrix that has no element. Here is the way I build up a synthetic sample. My synthetic sample is going to be defined in terms of the number of attributes we have. So R is the number of attributes or the space dimensionality. So if my space has just two attributes like temperature and moisture, for instance, I will select 2 over here. Observe this does not count the class attribute or the class column from my data set. It just counts on the attributes from the input space. So let's suppose my I is going to start as 1. So at first, I will build up my sample over here, varying from 1 to 1. And in that case, I will add up columns. C-bind means column bind, a concatenation of columns. So I will concatenate in my sample some Gaussian observations. I just define the mean of the average of this Gaussian function as 0, and we go up to, of course, our standard deviation equals to 1. So if my R is equals to 1, I will have something like this in R. I'll just produce a random sample with mean equals 0 and standard deviation equals 1, and the number of instances equals to I. If my number of instances is 1, I will produce just a single element. If it's like 10, I will produce 10 elements. But as you guys might notice, I'm concatenating along columns. So if I start with this new matrix, let's start with my new matrix sample over here. If I concatenate like this, sample receives itself concatenated in terms of columns with this. When I print my matrix out, it's going to have a single column, a single attribute. If my R is equals to 2, this will run once more, and I will have samples that belong to R2. So I have 2 attributes, 2 input attributes. So this guy is going to define that. If I plot this sample, you see my sample over here. Of course, I could plot using PCH equals 20. I think that's enough. Yeah, that's better to see all points. Of course, I could just restart, just get back and set sample equals null. And now instead of just 10 elements, I could come up with like 500. And once more, so now I will have a bidimensional, take a look, sample with 500 examples. If I plot it, it's going to be like a bidimensional Gaussian function. Yeah, so on top of that, we are going to build up some ways of shattering this sample. When I mean ways of shattering, I mean maybe a hyperplane could be passing along this place over here and dividing this maybe as positive and the others as negative, or vice versa, or maybe cutting here and dividing this half as positive, this half as negative, or vice versa. So that extract of my code over here is going to analyze how many different ways I can classify my space. How I'm going to do that? I will define some variable iteration over here, or iter 1000. So I will vary this from 1 to some number, some I, which is my sample size, powered to 2 times iter. Actually, you guys are going to see that this is just a way of making this code, or doing it, of running it like several times There is a big problem with my code over here, and the problem lies in here. If I define a small number over here, I will try not that many times as I should. If I define a very, very large number over here, I'm going to run this more times than necessary. And that's going to be a problem. So the point here is, it turns out to be impossible in practical scenarios to assess a big sample like this. You're going to see if I define a large number over here, but I will only have a very nice shattering coefficient estimation if and only if this number is really large. If it's large, this is going to be a nice estimation. If it's not, sorry, but it's going to be a far lower bound. So my point is, if we come up here with a quite great number, this shattering coefficient estimator is going to be better. It's going to be like closer to some tight lower bound, but in practical large case scenarios, it turns out to be impossible. We're going to wait like forever. We're going to wait like not just days, but like years, decades, and it goes on. You know, it doesn't stop running. That's a problem. Over here, I build up a hyperplane. This is the way we build up a hyperplane over here. I will define a vector, as you guys may notice, a vector W, which whose minimal and maximal values are -1 and +1. That means I will come up with some random values using a uniform distribution in this interval from -1 to 1. Okay. And the number of coefficients I need from a hyperplane are R coefficients. So if I've got like 2 attributes, I need 2 coefficients. Those coefficients are basically the ones that I will multiply by this first and this second attributes I have in my space. For instance, let's say I will come up with some with 2, of course, coefficients over here, like this. So 2 coefficients because I have a 2-dimensional space. Those are my coefficients. My point is, now I can multiply my sample by this vector. There is still something missing. I also need like some intersection point in terms of my plane. If I have a bidimensional space over here, my hyperplane can be cut in here, for example, like this, or if I increase some B or intersection point, it's going to intersect here or maybe here. Okay, so the like the derivatives of the hyperplane are the same, but the point they cut the space is different. So I need to produce also this B. And again, just getting back, I will come up over here with some B, and this will be my intersection point. What's the point here? That's the same as doing my W1 times something, times my first sample, for instance, the first element of my sample, plus the second element of my first sample times W2 plus B. So B is my intersection point, and I will have some result. Okay. So at this point, we will classify examples using a sine function like this. So I will basically multiply my sample by W, and sum up with B, and I will have a bunch of numbers. Those numbers indicate if a given point is on the positive or the negative side of my hyperplane. If I apply the sine function over here, you guys will see something like this. Most of those points are positive and some of those are negatives. Of course, I want to plot this once more. So I will plot my sample using colors defined by my sine function, but there is a problem with that. If I try to plot something that's negative, it doesn't work. So if I sum up 1, I will have everything that was negative is going to be 0, and everything that's positive 1 is going to be positive 2. However, 0 has no color in my plot. So I should sum up 2. So I could see that my hyperplane is crossing exactly this place, dividing this region with a given color and this with another color, as you guys might notice. If I come up with a different set of coefficients for W and for B, and I plot once more, my result's going to be different. My hyperplane will be in a different place. And that's the whole idea. I should come up with every possible classification, okay? Of course, it's just impossible because I should try this like forever, but let's start. So these labels, these variable labels, will provide the signs of the function, +1 and -1. So what I did was basically this. I just pasted all labels all together. By pasting, I did this. So I get the labels like this. Take a look. Those are the labels of this last classification we performed. Labels are here, positives and negatives. What I did over here with this paste was this exactly. Paste labels, going up, okay? Paste labels defining sep, or the separability or the separation, as hashtag, and collapse equals nothing, equals an empty element. This is going to put all those elements together like this. Okay, I think I did that. Yeah, that's what I did. Yeah. So I just took this as a key for a hash table, So in our case, what's going to be my hash table? It's going to be this list over here. So if I come up in my list and I say shatter, what's the name over there? Shatter.ways is going to be a list for me. And shatter.ways at this position is going to count how many times that particular classification happened. Or basically, if that classification has happened. If it has happened, I just count it. And next, what I'm going to do next is basically this. If I count how many classifications I have assessed up to this point, it's going to be just 1. So I can come up, of course, with a different set of coefficients for W and for B, and I assess the labels once more, like this. Just test the labels for me. Oops, here, okay. I have a different hyperplane now. Of course, I can paste and get a different key. If the key is different, when I apply that in my hash table, I'll just say, okay, now a different possibility has happened. If I count how many different classification ways I found, I will have 2. And that is happening inside this, okay? So this is counting for us how many different classifications we have. Of course, I did found like a classification in which every point on one side of the hyperplane is positive, the others on the other side is negative. But I didn't doubled this number because I'm just trying like as many classifications as possible. Maybe this is going to repeat once more, but just using the opposite sign. Having, instead of positives and negatives, negatives and positives for the same hyperplane. Of course, that's brute force. I know it, but no problem. We have to start somehow. And after trying so many iterations, and this is the problem, and now probably you guys notice this is going to be a problem, this term over here. I can just add that, okay, I can just say, for that sample size, the number of different classifications I found is this number. And I just add that in my matrix called Shattering, which started with new over here. This matrix has like every element I'm binding to this matrix, which is like a row, is going to be bounded, of course, along the rows of the matrix, and I return that. So if I load my code over here like this, just load it, okay, and I try to run it, like shattering coefficient estimator. Let's say I'm going to use this number of iterations, 1000. I will start with a single point in my bidimensional space, and I go up to 100 elements. The problem you guys will notice is this is a lower bound approximation. If I have a single sample, I will have two, as I showed you guys in the previous videos. If I have 2 points, I will have 4. If I have 3 points, I should have 8. But my number of iterations could only find 6. If I run it again, probably, or maybe it could find like 8. Yeah, this time it found 8. Wow, that's good. But this is going to vary. This is going to depend on the number of iterations I define, okay? Of course, I could define the number of iterations as 2 powered to n times something, but that's going to take like forever. Why that? Because that's a way of considering every possible binary combination, 2 powered to n. In this case, for 4, it's right, it's 14, and here too. For 5, it's also right, it's 22. For 6, if I'm not wrong, I think this is also right, 32. The whole idea here is basically this. I just leave this running like for a long period of time, like this. But there is a problem, of course. If I expect like to have all those results up to 100 examples, this is going to take forever, as you guys might notice. This is going to be like just impossible. It's not practical. But anyway, it's a way of estimating. So if I am assessing, for instance, for R2, let's stop like with 13, and let's set for R3 and go up to 13 as well. Something interesting had happened already over here. For 4 points in a 3-dimensional space, take a look. Yeah, I can shatter in all possible ways. In 2 dimensions I cannot, but in 3 dimensions I can. Take a look at how the number of possibilities has changed. Here we had 22, here 30. So we increase the dimensionality of our space. We're going to increase the complexity of our bias. So I'm going to copy this, and I will save in 2 different files. Sorry, my dog. R2. I'm going to save R2 over here like this. She's just crazy about the other dogs. Sorry. So I'm gonna cut this as well, and I will save it in a different file, r3.dat, as you guys can see over down here. Okay. So I'm going to save up like this. My idea here is to get out of those files and plot those files for you. I'm going to use gnplot because I know it's going to be easier. So r2.dat and r3.dat. You see that the complexities have changed, have significantly changed. I will plot using lines because I suppose it will be easier to see the results. Oh yeah. Over here, in this magenta color, we've got R2, and in green, we've got R3. Of course, if we increase the space dimensionality, the shattering coefficient is going to be more complex. You know what's interesting here? I can come up with some shattering approximation. I will start coming up with a second order polynomial to approximate R2, and I could use, could be this also a second order for the third, for the space with 3 dimensions. D, E, F, G, H. Of course, I cannot use like F and G here because they are function names, sorry. So I'm going to fit my function f of x on top of R2, dot that, via some adaptations in coefficients A, B, and C. And A, B, and C are here, okay? A, B, and C. Let's run it. Yeah, that's good. It's, yeah, the error is not that huge. It sounds like an interesting measure. Of course, if I replot my f of x, I'm going to see some approximation of my magenta curve. Yeah, it's a very good blue approximation over here. Oh, that's nice. So I could take advantage of this approximation, copy that. I could just save that in another file. I'm going to call it like readme. So for my R2 space, I have this approximation. So for my R2 space, my shattering coefficient will be my shattering coefficient for an n size sample, okay? Not 2n, but n, is going to be this A, which is like 0.94955 times n minus 0.650849 times n. Oh, here is n to the square, sorry. N powered to 2 plus 1.5035. And of course, for R3, we're going to have something different. Let's see the result for R3. So I will perform the same fitting over here for g of x on R3. Of course, my coefficients here are D, E, and H over here, okay. And we've got like, yeah, it looks like a good approximation by analyzing the errors over here. Let's see the plot. Yeah, after some time, you guys get used to see those coefficients. So over here, we're going to have 4.80869 times n to the square minus 28.1404 times n plus 40.958. Okay, that's good. Let's plot it and let's see how it behaves. Plotting g of x. Oh, it's a good approximation as well. Of course, here it's not, but over here it turns out to be, let's say a fair approximation. Not that good, but it's a fair approximation. Of course, to have like a very good approximation, I should have waited like for a long period of time to have the number of different classifications found for a greater sample size for both spaces, of course, especially for R3. That's good, but it's good enough for now. You know what's nice now? I can take those two shattering coefficients and start assessing what happens with my generalization bound. Let's suppose something like this. Let's suppose I'm just going to work. Remember, my generalization bound is this. my expected risk is smaller than or equal to my empirical risk plus some square root. This square root considers 4/9 times log of 2 times my Shattering coefficient function, like this, okay? But of course, for double, for 2 times the number of examples I have, minus log of some delta, okay? I'm going to Ctrl C over here, it doesn't matter. So that's the number I have. I'm just going to consider now, guys, that it doesn't matter this term. I'm just going to suppose it is like 0, just to assess this guy, how this guy changes, okay? In this case, I will do something like this. My sample size is going to start in 1 and goes up to like 10,000. And we will save up. Let's say here I'm working with a single dimensional space, okay? And here I will have 4/n log of my Shattering coefficient. Of course, this Shattering coefficient over here is going to be for my, I need to define it. We better define it. Better define like this. My ns is going to be the Shattering coefficient for the bidimensional space. Yeah, let's call like this. ns2 for the bidimensional space, and ns3 for the 3-dimensional space. Oh, that looks much better. Okay, guys. Yeah, that's fair. So I'm going to run like this, and then I will come up with my divergence term. You probably guys remember this is actually epsilon. So I'm going to have my divergence for R2 and my divergence for R3 for the 3-dimensional space. In this case, I will have the square root of 4/n times log of 2 times my Shattering coefficient. In this case, my Shattering coefficient is ns2, but actually it is for twice for 2n. So here I could do something like this, 2 times n, okay? And here I could do the same, 2 times n. Of course, the same is necessary for the 3-dimensional space. 2 times n. If you guys go back to the other videos, you see why it's 2 times n. It's because of the symmetrization lemma. And here we have minus log of delta. Let's set delta. I don't know, delta could be set up like 0.05. That's going to bring a 95% confidence in my uniform convergence, okay? And the same happens for my 3-dimensional space. However, I must use my Shattering coefficient for 3 dimensions. Okay, that's nice. So let's plot my divergence for R2. I have something. Okay, it's converging somehow. That's good. It's converging. And let's plot using, actually I should plot like using lines better. And I could use like a red line for my divergence considering the 3-dimensional space. Okay, both converge, but actually, as this is related to probability, I should consider just values below 1. So getting back to my plot, I should do something like this, from 0 to 1, and then plot using lines. As you guys might notice, of course, if I increase the number of dimensions I have in my input space, it takes more effort to converge. Okay? You know what's interesting here? Let's suppose I accept some epsilon equals to, I don't know, would be epsilon equals to like 0.01. You know what's interesting? Take a look. Do we have some epsilon, and epsilon is here, it is the divergence. Do I have some epsilon which is equals or smaller than 0.01? No way. You know why? Because this sample size with 10,000 elements is not enough. So what we should do? We should get back over here and run this again, but increasing our sample size. This tells us that even having a single hyperplane in my bidimensional or three-dimensional space, I cannot ensure this sort of guarantee that I wish. Having delta equals to 0.05, what means that in 95% of the scenarios I want to have this guarantee of 1% of divergence in between my estimator. What is my estimator? Is my empirical risk and my expected risk. So I should increase my sample size and go for it. Now if I plot it, take a look. Take a look what happens. Of course, it's going to take more time to plot. And I plot once more using lines for my three-dimensional space. I can't see the results over here. I don't know how they are. So I could just simply do something like this. What is the last divergence I found here for 100,000? Take a look. It's not enough yet. It's not enough in terms of this epsilon that I expect. Of course, what I need to do is, if I wish this epsilon as my guarantee of divergence in between my empirical and expected risk, I need to increase once more my sample size. I'm going to multiply it by 3. You guys might think, oh, so to have guarantees, oof, I need that. Oh, it's so complex to have a guarantee. I need such a large samples, large sample size. Yeah, you need it. Okay, let's deal with that. So let's see the divergence for this R2. The last one is going to be this. Oof, it's not enough yet. And for R3, it's going to be that. You guys see, okay, I can either increase my sample size, but let's see, my sample size goes up to 300,000 examples. I cannot have more elements. If I can't have more elements using this delta, which provides 95%, 95 because it's 1 minus delta, okay, times 100. Oops, 100 over here. Okay, guys, this that. Okay, 95%. I can ensure only those divergences. I can ensure that my empirical risk and my expected is going to be 2% far, approximately, of my expected risk in both scenarios. Of course, here a bit more, because this is like 2.06, and here is like 2.008. Okay, so if we increase the dimensionality, that's going to happen. We have another question over here. What happens if instead of a single hyperplane, I have, for instance, 5 hyperplanes? If you guys think about the multi-layer perceptron, for instance, the multi-layer perceptron considers an input layer that provides data to some hidden layer that provides results to some output layer. That's the simplest as possible multi-layer perceptron we can build up. Here, the number of neurons or units we have is the same as the input size. So if we've got like 3 dimensions, this is going to be 3. If we've got like a two-dimensional space, this is going to be 2. So this is the same as the input space dimensionality. Here is the number, basically, just going to the basics. This is going to be the same as the number of classes we expect to obtain, roughly, okay? I'm not worried about that at this moment. And this defines the number of hyperplanes cutting the space, cutting or shattering, if you prefer, the space, okay? So for instance, if I come up, if instead of a single hyperplane, I'm going to go back to this GNU plot as before. If instead of having, I'm just going to plot for you guys like this, I think it's nice, plot R2. This is R2 for us, okay? Using lines, of course, it will be good. If instead of a single hyperplane, I decide to use two hyperplanes and not just a single one. Again, f of x is an approximation, as you guys can see. If we have two hyperplanes, that's the same as every possible combination of two hyperplanes. If here I had a single possibility with one hyperplane, over here, of course, in GNU plot, I should use asterisk twice. I will have the result for two hyperplanes. Wow, take a look at the complexity I have. Here I have the complexity for a single hyperplane in 2 dimensions, and here for two hyperplanes in 2 dimensions. And of course now, for 5 hyperplanes in 2 dimensions. Take a look. I cannot even see the others. If I apply a log function here, I can. I'm just applying a log in this axis, as you guys might notice. Okay. If I try to use, instead of 5 hyperplanes, I'm going to use like 100 hyperplanes. Take a look. You guys might notice what's happening here. The complexity is increasing a lot in terms of the hyperplanes I'm adding up. So just consider now this scenario. I'm just going to go back to my shattering coefficient. Let's say here I have just one hyperplane. So it's going to be this. And let's see, instead of using this 3-dimensional space, I'm just going to clean it, and I will use the same 2-dimensional space, the same 2-dimensional space, okay, but using 2 hyperplanes. If I'm going to use 2 hyperplanes, that's the same as using this result powered to 2. Here in R, I use this circumflex to set up, okay, power to 2, or maybe power to 3, or power to 4, power to 5. That depends on how many hyperplanes you are considering. So my divergence over here for one hyperplane is going to be that, and my divergence for 2 dimensions but using 2 hyperplanes is going to be this one, and as 2 hyperplanes for the same delta, okay? When I plot this, you guys will notice the difference. TS.plot divergence 2. Oh, it's not divergence 2, it's divergence 2 for a single hyperplane. Okay, it's there. And now if I plot using lines, my divergence 2 for 2 hyperplanes, take a look. It changes a lot. It grows a lot. It's just impressive, as you might notice. Of course it converges, but it takes more effort in terms of my sample size. So eventually my sample size has to be greater to provide the same convergence as I do have with a less complex space of admissible functions. I'm just computing the space of admissible functions here, guys. Okay, I think this is enough for now. This is based on my estimation over here. Of course, this is a estimation, a far lower bound estimation, but there are some issues over here. It's a far lower bound estimation, but we are just assuming that every sample behaves like this. And all coefficients behave like this. Is that right? Is that fair? Oh no, because maybe I have some data set whose complexity or whose space organization of points is completely different of this. Or maybe the need for the hyperplane coefficients is also completely different. So this is going to change, and that is going to change as well. So it depends on the problem. As it depends on the problem, we're going to see in the next video that I've been studying that like for, I don't know, since 2012. Yeah, 2012, 2013. Yeah, 2013, I believe. And now we have a nice result that's going to be seen in the next video. See you guys.